Now, the work is defined, the work done by constant force defined as W equals force times the distance. And before we get going, let's see what the units for work. What's the unit for force? Force is what? Newton. And what's the unit for distance? Meter. So Newton meter. That's actually what the unit for work is, Newton meter. But James Prescott Joule did a lot of work actually on this subject, so to give him credit for that, 1 Newton meter is known as 1 joule, or 1 J. So we use J, or capital J, for joules, again, to appreciate what James Prescott Joule did on this subject. So 1 joule equivalent to 1 Newton meter. Now, if you take an object here and you apply a force of 10 Newton, and that object travels 2 meters, how much work is done by me? Because I'm the one who pushed the box. I'm putting a box on a U-haul there. What is the work done by me? The work done by me is the force times the distance. What was the force I pushed with? 10. And what was the distance traveled? 2. That is 20 joules. Now, on the other hand, if it's a big object, let's say it's one of those huge container, it weighs 1,000 kilograms, so it's a big container sitting on the ground, and I push on it with the force of 100 Newton, or 1,000, or 100. 100 Newton. I'm pushing, I'm sweating. For half an hour, the box is not moving. The box did not move. What is the work done by me? 0. So just because I'm sweating, my shirt's soaking wet, and I've been pushing for 2 hours, nothing moved, since the distance is 0, the work done by me is 0 joules. Now, change the story there a little bit there. Let's say we have, I don't know, something is moving in this direction, like a toy car. And it's moving in this direction. That's the direction it's moving. And you push down on it in this direction of a force of 20 Newton, and it moved all the way here. What is the work done by me to move the car? I'm constantly pushing down on the car, and the car keeps moving that direction. What is the work done by me?
If there's no distance, we can't figure it out.
Okay, I'll give you a distance. The car traveled. I forgot that part here. What do you want? Pick a number. 10 meters. Good. So what is the work done by me to move that car 10 meters?
On the second car, is that 20 newtons? There's a cord thing
yeah,
that's in the way.
20, yes, the same force. I didn't change my force. So I constantly, while the car is moving, I was pushing down. Yes?
Does it require a direction, like the force applied? Because if you were pressing down, I don't know, if you were pressing in the horizontal direction, then wouldn't the car move because of you? If you're pressing down, as the car is moving?
Well, the car was moving. I'm pushing on it like this. I jumped on it, even sat on it. The car still moves. My weight is actually my force down, but the car is moving that direction.
Wouldn't that be zero work done?
Correct, it's zero. Why? Because I'm pushing down, but I have nothing to do with the movement in that direction. I'm not the one who made the car go in that direction. That force has nothing to do with that. So the work done by me here, it's really zero. You're going to see we're going to change the equation in a second there. We're going to put the cosine of theta with it. So the work done by me here is zero because I'm pushing down over force of 20, but it didn't move in this direction. The car never moved in that direction. Zero distance, and that's why it's 0 joules. You're at the airport, another example now. And you got your suitcase with you on a wheel and it has a handle here. And you walk in, you're pulling behind you here, an angle, I don't know, 30 degrees, force 40 Newton. And that suitcase is moving right there. It moved, let's say, bless you, 20 meters. What is the work done by you pulling on that suitcase? How much work did you apply? Very good. 40, I think it was you, Alex, said 40 cosine?
Yeah.
Because what Alex is saying, the bag is going to the right. What portion of that force, what portion of this is pulling to the right? Well, the portion in this direction is actually the 40 cosine of 30 degrees. That's the piece that's pulling to the right. That's the one that made the bag move from here to there. So work is force times distance, and the force is what? 40 cosine of 30 times the distance traveled, which is 20 meters. So now I'll take my calculator here. Cosine of 30 times 20. Let me try again. 40 times the cosine of 30, I forgot to close the parentheses, times 20. And I got the work done is 693 joules. So the book decided, you know what, since it's going to be, instead of doing the component, let's change that equation now to the work done, instead of F times distance, let's call it, make it big here, the work done, it's force times cosine theta times the distance. Force times cosine theta times the distance. So if you go back to the previous example, what was theta here? What was the angle between the direction of the force and the direction that you're moving? You were pushing to the right and the thing moved to the right. So what was the angle? 0. What's cosine of 0?
0.
Cosine of 0? 1. That's why we use F times D. Now for this one, we know that works here. Now if you apply it to this one, what is the angle between the force and the direction that you're moving here? 90. What's cosine 90? 0. That's why this gave us a 0 value. So this works all the time. Now, I don't know how many of you actually like to work out, but when you go to the gym and you're doing weights, you lay on the bench and you push up, someone will come in, let's do a couple of negatives, come on. And what is that? Somebody will help you lift the weight up, and your job to bring it down slowly, right? Why they call it negative?
Because you're moving it down.
Exactly. Which way are you pushing? You're pushing upward, and which way it's moving? Down. So you are pushing, when you're doing this negative exercise, your hand pushing on the weight upward of, let's say, 200 Newton, and the weight traveled moved which direction? It moved down. Let's say half a meter. It moved down half a meter. So what is the work done by you? The work is force times cosine theta times d. Force is what? 200 Newton. Cosine, what was the angle between the direction you're pushing and the direction the thing is moving? You're pushing up, this is coming down. What's the angle? 180. Times the distance, which is 1/2. And guess what cosine of 180? -1. That's why the work done is called negative work. Minus 100 joules. So next time you go to the gym and you're on the bench press there, and somebody says there's some negatives, that's why they call it negative. Because you are pushing out and the weight is coming down at you. When you push out and the thing goes out, that's positive work. When you push out and the thing comes down, that's negative work. So with that in mind, then friction, we know friction if you're applying the brakes to a car there. Let's say we have a car here moving in this direction, and it moved, let's say, 20 meters, then stopped. Why did it stop? Because the friction force, right? Which way the friction force? Will be pointing backward, right? F friction. Kinetic friction. Let's say the friction force was 10 Newton pointing backward. What is the work done by the friction force? That would be F times cosine theta times the distance traveled. What was F? 10. What was the cosine of what? 180 times the 20. Cosine of 180 is what? -1 times 20, and that's a negative 200 joules. So the work done by friction is really negative work because the car is moving forward, your force, the friction force pushing backward, that's a negative force, 180 degrees. So your force, the work could be 0, could be positive, could be negative. Now here's a question. I told you I helped my son move this weekend from Washington to Pittsburgh. Let's use that. We have that U-Haul truck here. And the U-Haul truck has a ramp on it. And we had to move this box. This box along the ramp. The ramp has a leg L. Has a height H. We can use some numbers in a minute. We'll pick some numbers. So I can go push it up the ramp in this direction and calculate the work done by me. I'm pushing. This is the pushing force. Calculate how much work is done by me to move it up the ramp. Or I can take the box, if this is the truck here. These are the tires that, otherwise the tire's dangling in the air, right? There we go. These are the tires of the truck, Or I can take it and just pick it straight up there, move it up there, and put in the truck there. I can take the box and move it up there. The height H. Which one requires more work by me? Picking it up and putting it there, or push it up the ramp? Okay, let's look at this scenario. We're talking about, if we start the topic by saying the work done by constant force. So If you're looking at this box has a weight moving in this direction. The weight is what? The mass of the box times the gravity. If I pick the box and pull up with the same force, I'm pulling up, that's P. So me pulling up, moving at constant speed, that means the acceleration is 0. That tells me F, the net force, I'll just do it slowly to show you these forces are equal. The net force equals mass times acceleration. Since I'm moving the box up with a constant speed, my acceleration is 0. The net force is H minus mg, not HP. I'm using the letter P for force. I'm pulling on it. P minus mg equals the mass times the acceleration, which is 0. That tells me the pulling force has to equal to the weight of the box. So how much work is done by me to move the box from here to the height of the truck? It's the force times the distance, times, if you want to put cosine theta, go ahead. My force pulling upward was the mass times the gravity. That's what P is. Me pulling on the box upward, that's why I called it P. Now, the distance traveled is H. And the angle is what? 0 degree? I was pulling upward and the box moved which way? Upward. So the angle is 0. That's a 0. Cosine of 0 is 1. So the work done by me is mass times gravity times height. Now let's look at this case. If I push on the box, let's say this angle is theta here. I push on it in that direction. Now again, the box is moving upward, let's say constant speed. Both cases I'm assuming constant speed. We know there is a force in this direction equals mg sine theta. And I'm pushing the box up that ramp. So the box is moving in this direction. And Newton says if the box is moving, the net force equals mass times acceleration. If it's going up the ramp, the reason it's going up the ramp because this force P is going that direction. I need to subtract from it mg sine theta. Should equal the mass of the box times the acceleration, which is 0. That tells me my pushing force for this scenario is going to be equal to mg sine theta. So what does that mean? My pushing force or pulling force is mg. That's heavier. This is actually less. I don't have to push that hard because of sine theta is always less than 1. So that's the advantage of having the ramp. But in terms of the work I did, the work is I'm going along this distance now. So how much work done by me? It's the force times the distance times cosine theta. Now think about it. I'm pushing in this direction along the ramp, and which way the box is moving? Along the ramp. What's the angle between them? 0. So the force is mg sine of theta. Travel distance L, from here to there is L, I call that L, times cosine of 0. So what is that equal to? mg sine theta times L. Now let's take you back to geometry. The sine. Sakatoa, remember Sakatoa? The sine, when you have a triangle, the side is opposite over what? The hypotenuse. That Jason will be the tangent. opposite over the hypotenuse. So sine of theta really is equal to the side that's opposite to the angle, which is h, over the hypotenuse, which is what? L, and you're going to multiply it by L. And what's going to happen to the L's? So what's the result? So guess what? If you pick it up, put it in the truck, or you push it along the ramp, the work done by you is going to be what? The same. I call it case 1, case 2. So the work by case 1 is equal to the work by case 2. It doesn't matter if you use the ramp or not. The only difference the ramp does, it makes the force smaller. Because if this angle, the smaller this angle, the longer the ramp, is the smaller the angle, and the cosine gets much, much smaller as the angle gets smaller. So all that does, the ramp really makes it, you don't have to push that hard on it, but you got to push it for a long time, so the work done by you is still the same. But it takes a little bit longer, you know. So in this case, regardless which one you do, the work done, it's mg times h.